So I'll talk about the assume guarantee reasoning environment, or agree. And the first part of the talk, I'm just going to do a really high level overview of what kinds of analysis you can run, what is the environment, what can you do with it. And then the second half of the talk is going to be a demo. So I'll show you how to take an AADL model, annotate it with the agree contracts, and then run the analysis on it, understand what you're getting back, how to read the results, and how to adjust the model to if things start to fail, things like that. So, system development. If you are developing a system, there's a number of ways that you can go about doing it. And one of those ways is called model-based system development. And the idea is you create this model, which is a representation of your system, and then base the development cycle of the system around the model. So you can do things with the model like simulation, analyses, testing, things like that, and then adjust the model if there are problems and continue with the development cycle. So a model is just a representation of the system. And what you want is that representation is as close to the system as it can be, given that it's a representation. And there's a lot of ways that you can build models. So a common form is graphical. You could even write a PowerPoint slide that represents a model or a system. You could use SysML or FACE, which are graphical representations. Or you can do something more textual like AADL. You have seen examples of this modeling language where it's more like code that you're writing. But in all of these cases, to perform any kind of formal analysis or model checking, you have to be able to take the model and represent it mathematically so that you can look at the mathematical representation and run analysis over that. So what you need to have is sufficiently well-defined semantics in your model so that you can represent it mathematically so that you can run analysis on it. So when I talk about analysis over a model, part of that are what are called specifications. And that's just when you have a system requirement, you want to translate it into a formal logic statement. So the example I have here, the requirement might say, if the temperature surpasses a given threshold, then the system shall shut down. That would be a requirement. But you can't run mathematical analysis over natural language, so what you would want to do is take that requirement and specify it in formal logic. So then this is an example of linear temporal logic where it just says G, the G means globally in all states. If the temperature is greater than the threshold, then in the next state, the system shuts down. That would be a specification. So what model checking is it's an automated technique that shows that the model, the mathematical model, satisfies the specifications that you have. And if the model accurately enough represents the system, then you would hope that the system also satisfies its requirements. And in model checking, what you want in the end is some proof that shows in all states the specification holds. So that's the goal of model checking in a nutshell. One term that I'm going to use often is called a contract. And if you have a component defined in a model and you have a contract on that component, what that is just an agreement between the component and the environment in which it lives. So contracts can contain various things depending on what you're talking about, but a really good way to look at it is preconditions and postconditions on methods. That's a contract. So you have parameters coming in and you might have preconditions saying, I'm expecting these parameters to be a certain thing or fall within some range or what have you. And then the post conditions say, and I'm guaranteeing that at the end of this method, these things will be true. So that would be a contract for a method. In the assume guarantee reasoning environment, the contracts contain what are called assumptions and guarantees. So the assumptions are on input, kind of like preconditions on parameters, and guarantees are on the output. Here's an example of an agree contract. So we have an AADL component, which is a temp sensor. It has an input and an output as features. And then the agree contract goes inside of that AADL component, and it has an assumption. And that assumption is on the input. It says, I'm assuming that my temperature when it comes into this component is going to be within this range. And then the guarantee is on the output. And it says, as long as my assumption is met, then I can guarantee that this is going to be the behavior of the output. Now, what you can think of this as a, I'm going to narrow the scope to a component. You have your assumptions on the input, you have your guarantee on the output. And how you can think of this from a component's perspective is if the assumptions are true up until now, this current instant, then the component output is guaranteed. So that's from the component's perspective. But we have an entire system. And in AADL, there are layers of architecture. So you have the top level, you have subsystems and subcomponents beneath that, all the way down to the leaf level components. And assumptions and guarantees can be on any of these things in any of these layers. But how you can think about this when you're modeling with agree is assumptions will always imply lower level assumptions, and guarantees will support higher level guarantees. Another way you can think of this is assumptions will imply downwards, down the hierarchy of your system model, and guarantees imply upwards. And once we get to the demo, I'll show you an example of this so you can see exactly what I mean by the assumptions implying downwards in that in the model that you have. So this is a very rough sketch of what the agree implementation looks like. All the way on the left, you have the AADL system model, and that would include your types, implementations, what components you have, all of the connections. Then you would annotate that with contracts. So that's the agree annex. That goes through parsing. An agree program is created, which is an abstract syntax tree in Java. And then that gets translated into what is called Loose, and it's a data flow programming language. And that is fed into the JKind model checker as input. Then the model checker does its magic, and then the results are displayed back in OSATE where you started from. So what we see as a user is the AADL system model, the agree contracts, and the results displayed all in OSATE. All the rest of this is just behind the scenes, what's going on. Now in agree, there's a number of different kinds of analysis that you can perform. And I want to talk about a couple of them that are very important for what we will be showing in the demo and often is what agree is used for. So first there's monolithic verification. This tree structure that I have is a representation of your system architecture. So you have the top level, it has a couple of subsystems as children components. They have some subsystems as children components and so on. And what monolithic verification does is it takes all of the contracts that you've defined for every child in the entire system. It flattens the model and it uses them all to try to prove your top level properties that you have for your system. So this works really well until you get a very, very large system. And as you can imagine, the number of contracts that you have gets really big really fast. So what they introduced to address this is called compositional verification. And what the idea is they take a very, very large problem and proof and break it up into a lot of small ones. So first, just look at the direct children. Take those contracts and prove the top level or the parent level properties. So that's a smaller proof. Then after that, take the children beneath that one and prove one level up, and so on all the way down the architecture. This is what compositional verification is. So it breaks it up into a per layer kind of analysis instead of flattening the whole thing and making one giant proof out of it. So this addresses some of the scalability problems that show up in monolithic analysis. When you have a really big model, you can break this up. So the example that I will go through in the demo, you've seen before, I briefly went through it with you. This is the sensor system. So let's say that we have 3 environmental inputs that we need to watch for in the system. There's pressure, radiation, and temperature. And this is the top level is the sensor system. And each pressure, radiation, and temperature is its own subsystem that monitors those environmental inputs. And so there's sensors inside of those that say, well, I'm gonna watch the pressure and send out a high indicator if it surpasses some threshold that we have set. And if it does, then we want to shut down the system. So that's the main idea of what's going on in the model that we'll look at. So since AGREE looks at contracts and writing contracts, we have to know what are the requirements of the system. So at the system level, so that's the top level of the hierarchy, what we want is that if temperature, radiation, or pressure is above the threshold, then we shut down the system. That's the behavior that we want as a system perspective. At the sensor, so if you remember the hierarchy, the sensor is the leaf level component. What's its requirement? Well, the sensor needs to report a high value when whatever it's measuring in the environment surpasses some threshold. So you can see the top level has its own, even down to the leaf level has its own. So those are the requirements we want to look at. But what about the assumptions? What can we reasonably expect from the environment? And one thing I do want to say is that it's really sometimes kind of tricky. In this example, it won't be tricky to come up with a good assumption that we can make, or at least decent enough for the demo. But it's hard to come up with a reasonable assumption because your assumption, if it's no good, you can assume anything. And if it's false, whatever follows is true. And so you have to be really careful with how you work with your assumptions when you're modeling in AGREE. Hopefully today in the demo it won't be too tricky, but keep that in mind if you're ever trying to think about the environment of your system and what your assumptions are. Can you give a good reason why you're assuming what you're assuming? That's an important thing to keep in mind. So now we want to go to a demo. So let me share my screen. Here is the sensor system. So this is the top level in AADL. We've got a sensor system. It has 3 input ports. These are the environmental inputs that I showed you before. And then there's a single output port, and that's the shutdown command. Now, there is an implementation. You can see here we've got radiation, pressure, and temperature. These are subsystems. So these are children level subcomponents. And all the connections are there and so on. So now, what I want to do, I have my system and I want to be able to reason over the interface. So those would be the inputs and outputs. So if I know that assumptions imply downwards and guarantees imply upwards throughout the system, and I know that at a component level, if the assumption is met, then the guarantee holds. So the first thing that I usually start with when I'm modeling in AGREE is assumptions, because I can start at the top level and write out my assumptions going all the way down the hierarchy, and then add in the guarantees from the leaf level upwards, and you've got the assumptions that you need in order to, excuse me, in order to make sure that your guarantees hold. So let's start with an assumption at the top. What is a reasonable thing I can expect from my environment? I'm going to narrow the scope of this a little bit, and we're just going to talk about temperature. I'm going to ignore the other 2 subsystems for now. We'll just focus on temperature for simplicity. I've also got some constants defined in the model. So I know my temperature threshold is 300 degrees Celsius. So this is true. I can use this constant anywhere in the model. And I will write down the first assumption for us. So I want to assume something about temperature. Is within reasonable bounds. Now, this very much depends on where you're running your system. What does that mean for the temperature in the environment to be in some reasonable space? Well, are you running it, the system on planet Earth? Are you running it on Mars? It depends on your environment, really. Let's assume, just for the example's sake, that your environmental temperature is always greater than or equal to 0 degrees Celsius, and it is less than or equal to 600 degrees Celsius. So now remember that my, I'll just add this in here. Oh, I didn't copy the whole thing, of course. This is all in Celsius. So those are our units. And my threshold is at 300. So we've got our first assumption. We know what our threshold is, which we'll probably be using more in the guarantees because that's gonna come into play then. The next thing that I want to do, I've got my top level assumption. Now I want to start looking at the children because I know that the assumptions imply downwards. So if I'm ignoring everything else, I want to look at my temperature subsystem. So if I go to temperature control, I've got the temperature coming in and I've got a shutdown command going out. Assumption is on the input. And I know at the top level, my assumption says that the temperature, a reasonable range for the temperature is between 0 and 600 degrees. If it's outside of that, I'm assuming that something went wrong with my sensor or who knows what's going on, but for whatever reason, the environment I'm in, it should be within that range. So what kind of assumption can I put on this temperature coming in? Anyone have an idea? No ideas. Or nobody wants to say anything. That could be too. So if I have at the top level that my temperature comes in within these bounds, that connection just goes straight from the top level into the child. So it should be the case that it has the same reasonable bounds at the child, which is the temperature control. So really what I can do is I can just say, well, I'm going to have the same assumption here. It's not going to be any different. My temperature coming in should still be within some reasonable range, which is the same thing. Okay, so let's pause here because I've got my top level and I've got my child level. Now this also has a child. This has a temperature sensor child component. But what happens if I run analysis now? So I've got an assumption at the top two levels. So let's just do that. So to run analysis, you would select the implementation of the level that you want to look at. And you would go to agree in the analysis menu. And I want to just verify all layers. That's the compositional approach. You see here monolithically, that's if I want to do a monolithic, but I just want to do compositional for now. And what happens is, here's your agree results. And you can see the verification, the green checks are a good thing. And you have your contract guarantees. So I selected the sensor system implementation. The contract I have defined is at the top level. And it says, here's my assumption, temperature is within reasonable bounds, and that is met. Okay, so that's what it looks like as you start adding in assumptions. So let's go to the next child. At the sensor, here's the temperature sensor. Temperature comes in, high indication goes out. What would be my assumption here for the temperature? Because I'm dealing with inputs right now. guys are quiet.
Would it be the same assumptions from the higher levels?
Yep, exactly, because we're still looking at temperature, and there's nothing that's happened to that input on the way through. So far, it's just getting passed along. So there's no computations over it, there's no changes to it, or shouldn't be. So we can still assume that same range that was on some of the higher levels. So that is correct. Oh, of course, name change. Okay, so now I've got my assumptions and I want to start looking at my guarantees. So if we remember what I talked about before, how guarantees support higher level guarantees, what happens in that compositional analysis is that when you're at a given level, you're trying to prove the parent level guarantees. And it goes to the children and it says, does the guarantees that are defined in the child components, can I use those to prove the parent level guarantees? So usually when I start modeling, I start at the leaf level and I work my way upwards. And I run analysis with each layer to make sure that my child level guarantees actually do prove the parent before moving to the next higher level. So what I have at the sensor, I have a high indicator value. And I've got temperature coming in, and I know that my requirement says, if this temperature surpasses a threshold, then I want my output to indicate that it is high. So that's it in natural language, but I need to translate that into logic so that it can actually be done, the analysis can be done mathematically. But I can write down what I said. If the temperature surpasses threshold, then indicate high. Okay, so how can I write this so that Agree can perform reasoning over it? And I'll remind you that I have these constants. So here's my temperature threshold. I know I can use that. So that's when we hit 300 degrees Celsius. So how would I say if temperature surpasses threshold? Well, then what I would say is just that temperature is greater than whatever threshold I have, right? Temperature greater than threshold. Okay, so there's the antecedent. Now, syntax-wise, this is the implication symbol. What's my conclusion here? Oh, I did the wrong thing. This should be, now it's trying to automatically tell me what I should do. There we go. Then indicate high temperature. So my high indicator is a Boolean output port. So if my temperature is greater than the threshold, then high indicator equals true. Okay, so now I have my guarantee at the lower level so that if my temperature gets above the threshold is given, then I should output a high indication. So the leaf level is done. Now I need to move up to the parent level. And so the parent of the sensor is the temperature control. The reason why that is you look at subcomponents, you see sensors, temp sensor. Okay. So I want to add a guarantee here. And that guarantee is what? Well, I have temperature coming in, and the job of this subsystem is to send a shutdown command to the top level. So what I want to say is that if I surpass the threshold, then I better have a shutdown, or I better send a shutdown command. So how can I say that in logic? Guarantee any takers?
I mean, would it be kind of the same as the last one? Like if the temperature is higher than the threshold, but then the Boolean shutdown equals true?
Yep. Yep, very much so. So if I have environmental temperature greater than temp threshold, then what? In this case, we would have shutdown. So I'd want to say shutdown equals true. Did I spell something wrong? I might have spelled something wrong.
I think it's your indicator. It should be a hyphen instead of a equal sign. Like the arrow. Or maybe not. No.
No. It's with constants. Okay, well, when in doubt, clean your projects, right? That's always a good thing to remember when you're working in OSATE, is if you start getting syntax errors, clean projects, that sometimes is helpful. Okay, that still didn't seem to work though. So I have constants. Well, here's an easy thing to do. I know my threshold is 300, so I'm just going to put that in. I'm not sure why it wasn't including it, but there, problem solved for the demo. So what this says now is that the environmental temperature surpasses threshold, then my system shutdown command is true. Okay, well at this point, I want to run analysis because remember how compositional reasoning takes it one layer at a time? So I'm in this temperature control system and it has a child. I want to make sure that my child level guarantee supports my parent level guarantee. So what I'll do is I will go to agree, verify all layers. I could do single because I know there's just one layer beneath me. And what I get for the results is that it passes. So I know that my child level property was enough to prove the parent level. Now, what could I do to make it so that it wasn't enough? Like, what if I said, well, at the parent level, my environmental temperature surpasses 400. Then I send a shutdown command. What happens then with my analysis? Well, if you think about how the implications work, why is it that it passes? If we look at the child sensor, this threshold is actually 300, right? I can put that in from this here, 300. So at the child, it says if it's greater than 300, then I'm going to send it out. At the parent, it says if it's greater than 400, I'm going to send it out. Well, what happens is that if the environmental temperature surpasses 400, the child has already sent the shutdown command, the high indication. So we're safe. That would be why at the child level, I had a stronger constraint. So that proves the parent level, even though the parent level had a weaker constraint. Now, if we went the other direction, there would be a problem. Okay, so I want this to be even weaker. So now this says that the parent, well, if the temperature surpasses 200, then I want this shutdown command to be true. So now if I run analysis, what happens? Now I have a problem. So the red exclamation point is the problem. I can't prove it. So now it links to this guarantee here. And it says, well, you wanted to prove this, but I can't. And one thing that you can look at is what's called a counterexample. And what it shows you is valuations for everything in your model in such that the property can't be proven. So it gives you a trace of the states in which you can't prove it. So let's just look at it in the console. So now this is at the temperature sensor. Temperature is 201. That's the input. And at the sensor, it said, well, I'm within the ranges where everything's fine. I'm not going to output high indication. So everything in the child component is working fine. But at the parent level, the environmental temperature is over this threshold, but the shutdown command is false. So you can see how the child guarantee needs to imply the parent guarantee. So the constraint at the child needs to be either the same or stronger than at the parent. So that gives you an idea of what the analysis results look like when you fail to prove. We'll put this in correctly. And then we move up a level. So now I know that with this, everything proves. So now I can move up to the parent level. Now at the parent, I'm looking at just a slice of that architecture. So I have the top level, and I use just its direct child to prove that guarantee. So it's only going to use the temperature subsystem. It's not going to reach all the way down into the sensor. Nonetheless, I want to write a guarantee. And the guarantee is going to be a restatement of that system level requirement that I showed in the PowerPoints that, but if any of my environmental inputs surpass a threshold, then we shut down the system. In this case, I'm just looking at temperature, but still same thing. If temperature surpasses threshold, then system shall shut down. For the sake of a simple demo, again, you're probably thinking, well, isn't this the same thing? And yes, it really is. Just to make it clear what's going on here. So if this is greater than the threshold, then shutdown command. So now that I have all of these going, well, the first thing I would do is make sure that my layer proves. So what I can do there is just select the implementation and go to verify single layer. So all that's going to do is it's going to look at this system and its direct child or children and make sure that my guarantee proves with that one level. It does. And so then I can combine that into a full analysis of the whole system and verify everything. And yes, I do have that it proves. Again, what you could do is mess around with these numbers just to get an idea of how the constraints at the lower level affect the upper levels, but we did that with the last layer. It'd be the same here. So this is an idea of how you can go about adding in those contracts and making sure that things prove. Now, if you were finishing up this kind of example, what you would want to do is extend this top level guarantee, because the system is in terms of 3 different inputs, right? Or up here inputs, radiation, pressure, and temperature. So you would want to add those values into the assumptions, and you'd want to extend this guarantee so that it talked about all 3 of those thresholds being passed. If any of them did, then we would want to send a shutdown command. So once you add everything in for all of the children's subcomponents, then you'd want to adjust this top level a little bit. But You get the idea of how to add those in, how to run the analysis as you go. I would say if you're ever going to annotate a model with agree, don't throw in everything at once and then think you can prove it. Most of the time you can't. I've tried. And it's best to just go in a step-by-step fashion so that you can see if you run into a problem, what was the problem, and really think about how the children layer guarantees affect the proof at a higher level. So with that, I've got a couple more things I wanted to say with regarding agree, because there were other analysis options. So when you went to the menu item for analysis and you went to agree, there was the verify single layer, all layers, monolithic, and then there was a couple other options on there. One of them is realizability. And what that means is that within a component contract, what you have specified is actually possible. It's realizable. This is a component level analysis, so it's just going to look at the component itself. But if we look at this example here, what about this contract is not possible? Well, if you look at these two guarantees that I have, one of them says that the high indication is true if temperature is greater than the threshold. And then the other one says that it's true if the temperature is less than the threshold. So there's a contradiction there. You can't have both being true. It's like saying A and not A. It's not possible. So realizability looks at it from a component contract perspective. And then consistency looks at it as a system-wide. So all of the contracts are logically possible as a conjunction. So if you take everything that you have in your model contract-wise and put an and between them, it is possible. So that would be another thing that you could check. If you have a very large model, you could have a lot of contracts for different subcomponents that maybe aren't used in a proof of one of the properties that you want to prove. And you might ask the question, well, what's the minimal set of things that I've specified in my model that are actually used to prove the property? And that you can also get using agree. This is called set of support in the user menu, otherwise known as inductive validity cores. There's a couple of things that I wanted to point out specifically agree is not used for and is not conducive for. One of those is state machines. So within a component, there are a number of states and behaviors that you could describe. Agree is not good for that. Agree has its contracts over the interface. So that would be the inputs and outputs. And to try to reason about the internal state of the component is not what it's made for. Another thing that you have to be careful with is what's called liveness properties. A liveness property would be eventually something happens. So in the model or the examples that I've shown and the model that I've shown, I've used safety properties, which is this does not occur. Okay, that's a safety property. A liveness property says sometime in the course of the lifetime of the system, this thing will happen. And that is not supported using agree. So what you can do is use past time LTL. So you can refer to 2 steps ago, something happened. Now I'm in this state. Okay, that's fine. But eventually statements are not something that you can reason about.